Hello and welcome to the EBN EBN semester / exam preparation course. In this video, we're going to be covering typical questions you're going to be seeing in a semester test 2, and yeah, we're going to be going through the questions. So the first question we look at is this question here. It says that you should simplify the circuit A with source transformation so that it looks like the circuit B, and determine the values of R and A and B. Okay. So AI1 plus B. Oh, okay. So first of all, what we want to do is we are going to have to start by source transforming this part, because we've got a parallel circuit happening there, right? So for us to be able to now determine the new voltage, V is equal to Ri, which is 0.2 I multiplied by 7K. This gives us 1.4K. 1.4K I1. Okay. Right. So then this transforms the circuit into this diagram here. There's your 7K and your source. Wait, why did I do two pluses? Weird. It's plus on that side, minus. And that's your 15. Okay, so now you are going to combine these two together. Your source, your dependent source, and your voltage source. So therefore, now what you have is this. Your 7 and 13 together make 20K. So that's 20K. And then now your source. Okay. So you are going to have this here as 15 minus 1.4K I1, right? You may ask yourself why we are taking it to be 15 minus, right? So the reason for this is that we are looking for a current source that points up, right? So we need to make our new dependent source. We need to make sure that the current is going to flow in this direction. So therefore, that's why we said 15 minus that, right? You could have said it's equal to 1.4K minus 15 if you decided to draw your current source looking down, right? That is the only reason why we have it as 15 minus in the specific order that we do, right? Okay, so then after that, now you are going to be source transforming this back to, you're going to be source transforming it into a current source, right? So your I is V over R, which is 15 minus 1.4K I1 divided by 20K, all right? And this is something that you can literally punch into your calculator. This is where you now will be able to determine your value for A here, because your A value is the coefficient of I1. So your A value and your B value can be determined from this, and then your R value is 20K. because after source transforming it, that's your 15K there. You'll have your 20K there, and then you will have your current source like that. And yeah, that's the first question. The next question that we will be looking at is this question about your Thevenin equivalent voltage V of TH. So they ask you to find the Thevenin voltage and Thevenin resistance, right? So because this is semester test 2, this is where you start to expect to see dependent sources, unlike in semester test 1 where all of our sources were independent, which made it very, very easy. Okay, so we are going to first start off by finding our V Thevenin, and remember that our Thevenin voltage is the open circuit voltage between the two nodes, right? Okay, so let's to find our thingy. This circuit actually looks a little bit scary the way they drew it, so I'm going to draw it in my way to make it actually look a little bit more palatable. Don't know how to pronounce that word, but that word. So this is your one source, your one terminal, and this is your other terminal, right? I think it looks better like that, right? So now you can see, so now it's pretty simple. You can see that your Thevenin voltage is actually the voltage across your 3K resistor plus your 2K resistor, okay? So you can simply start by doing a KVL, right? So you've got your 1K, you got your 3K, you got your 2K, and you got your 15K, right? That is all being multiplied by the current I, alright? And this is equal to, because we are going through it like this, right? You will see that this is equal to 3V1 plus 15, right? But, so, now we have two variables. We have current I and we have voltage V, right? So V1 is the voltage across our 3 kilo ohm resistor here, right? Which is Ri, so therefore it's 3Ki, right? So therefore now you've got this whole thing is 21K. I is equal to 3 multiplied by 3K I plus 15, which is 9. So you got 12K I is equal to 15, so therefore your current is equal to 15 over 12, right? And your V of Thevenin, VTH, is equal to 15 over 12 multiplied by 3 plus 2K. Well, 15 over 12K, my bad. Forgot about that K. 3 plus 2K. So that cancel out. So that's like 5 by 15 multiplied by 5 over 12. And 25 over 4. 5 over 4. That's a pretty decent looking number. So if you want the number itself, it's 6.25 volts. Alright. As we said with the semester test 1 questions, you are looking for round, beautiful looking numbers. If you had your answer, like if you were very much in a hurry and you see this 15 over 12 and like if you look, what was I gonna say? Things that happen. Okay, now. So as we said, remember that our final answers should look like beautiful numbers. Like that's the way it is in EBN, because you guys still have your training wheels on. They're giving you guys very beautiful looking circuits which do not exist in real life. So yeah, lucky enough, this is your answers are always going to look like proper numbers. Okay. So now we need to find our Thevenin resistance. So for us to find an equivalent the R Thevenin, we need to add a test source because we have this dependent source in our circuit, right? So when you look at this, you might ask yourself, should I use a current source? Should I use a voltage source? You know? So whenever it comes to this, I always look at whether the dependency is on a voltage or a current, right? So you can see that this is 3V1 and this is V1, right? So therefore, it would be better if you use a voltage source here, right? The reason is that now you can easily determine the value of V1 because you use a voltage source. But if you had decided to use a current source, right, what you would do now is that it would be a little bit more difficult because like the current is flowing through here, through the resistor 1, and resistor 1, right? It's flowing through like that. But also, what happens is that the current, some of the current flows back in here, while the sum of it goes through the 15K and then goes through the whole loop and goes into the 1K, right? So if you chose the current source, you would have a lot more work on your hands, and I'm not even going to attempt to do a current source version because it would be it would not be fun at all. Okay. So let us now determine our voltage. Okay. So our Thevenin resistance. So first of all, since we chose a voltage source, we need to determine the current that is flowing through here. IT actually, because test source shouldn't be IO. IO is output. IT. T. Yeah, looks better. Okay. So first of all, V1 is equal to 1 multiplied by 3 over 3 plus 2. This is simple voltage division, alright? This gives you a value of 0.6 volts, right? Pretty simple. So now that you've got a value for V1, right, you can now try to determine the current that is going through this node, right? Okay. So let's quickly draw our new circuit, right? So now what we have is we have this going on. We've got a 3 by 0.6 is 1.8 volt source, right? And then you've got a 16K, so 16K resistor, which is just a 15K and the 1K, alright? This is, should delete that and draw it there as IT. Okay. Wait, undo. Okay, so here. Oh, why was there one resistor there? My bad. It's supposed to be 2, because you got your 3 and you got your 2, and then there is your voltage. Okay. So now, what I'm going to do is I'm going to source transform this part, right, so that it becomes a current source. Okay. So as a current source, we have the value of 1.8 over 16K, right, and it is parallel to our resistance of 16K, and then you have your 3 and 2K respectively, And then you've got your V of test, right? That is what is happening, okay? So what happens is that the current formed here splits into here and splits into here, right? And the same thing happens with VT, that it splits into there and it splits into there, okay? So this would mean that it would obviously be good if we found our parallel of 16 and 5. So 16 by 5 over 16 plus 5. So when you've got 16 in parallel with 5, this gives you a value of 80 over 21 kilo ohm, right? So your circuit looks like this now, 1.816K. So it's 80 over 21. So this is VT. Right. Okay, so now, first of all, we know that the current I of I'll call this of 1, I1, right? I1 is equal to the voltage VT, the voltage across it, divided by 80 over 21K, which is 21 over 80 milli. 21 over 80 milliamps, right? Okay. And by the way, I just typed this into my calculator. 1.8 over 16K simplifies itself to be 9 over 80, right? So therefore now you know that that this current source produces 9 over 80 milliamps, and this is M, milliamps, and the current going through this resistor is 21 over 80 milliamps. So therefore the remaining 12 over 80, so I of test is 21 over 80 minus 9 over 80 milliamps, which is a value of 12 over 80, right? This is your value of IT, okay? Okay, so oh, okay, I don't have empty space there. I'll just do a little bit of erasing here and do my final answer here. Didn't think it would take this much space actually. So now we have enough information to determine our resistance, our Thevenin resistance, right? So our Thevenin is V over I, which is 1 over 12 over 80 M, millis, remember, M, which, funny enough, becomes 6.6667 milliamps, which is just, not milliamps, it's kilo ohm. Why am I saying milliamps? So it's 6.66. What am I doing? 80 over 12. Yeah, it's equal to 6.667 kilo ohms, right? If you put in 80 over 12 into your calculator, that's what you get. You get it's equal to 20 over 3, which is, it's not a beautiful number, but it's still an okay number, you see. 6.667 is you know, it's not like an absurd number you've never seen before in your life. It's not a particularly beautiful number, but it is a whole number. Not a whole number, I mean a whole. It's not an evil looking fraction, it's an okay looking fraction. So this is the next question. They want you to do a Norton equivalent now, and they want you to find the current IN and RN. And in the test there wasn't these red lines here, right? That came with the paper that I had. There was a lot of writing all over the paper, and I had to do a bit of erasing, and that's as much as I could do. Okay. So, lucky enough, there's no dependent source. Okay. So finding our Thevenin resistance is going to be pretty simple. So we first start of all by switching off the sources. So remember how your voltage source becomes a short. So this is now a short, right? So now you must find the resistance between those two nodes. So let us draw this circuit and try to determine this equivalent resistance. Okay. So first of all, we have our 6K here. Well, actually, it's 12K. 12K is 6K. Then you got 6K and a 12K. Then these two are connected to each other. And then these are now connected like this with a short. Okay. Okay, that's gonna be a little bit annoying. I guess that's why it looked a little bit simple. So I would like you to take a moment to look at this, right? So you've got one node here, right, shared in between there, as per seen as it is your node A. As per seen, what am I saying? Okay, and then you've got your second node here, right? So basically what you've got is you've got just taking a chop out of this. You got, let me use the same colors. There's this red spot, and then you got a 12K. Nah, I didn't draw it nicely. Your 12K there, and you have your 6K there. I just redrew that corner, right? So now you can see that these two, the 6K and the 12K, are actually in parallel. So 12 by 6, it's going to be 12 over 4. Because I mean, this is something that you learn throughout doing enough problems. When you've got a ratio of 1 to 2 between your resistors, you take your highest resistor and you divide it by 3. So 12 divided by 3 is 4. You can do you can punch it into your calculator and double check. I've been doing electronics for long enough to know the shortcuts. So your 12 in parallel with 6 becomes a 4K. Alright, that is what that is. Okay? So that's a parallel result of those two. And the same story that we just used to find our parallel resistors there, here we are going to use the same sort of story. Now instead I'm going to use black to show you that the same logic actually applies, right? So there is the node that was in purple, but now I wrote in black so that you can see that we can use the same steps that we were using. And there is the yellow, right? So everybody would agree with me that the same analysis we applied to say that those two are in parallel also applies here, right? So therefore now we know that these two are also in parallel, the same way that those two were in parallel. It's a bit of a mind tweak, like sometimes it breaks your brain a little bit, and then you just need to you have a little bit of a glitch every now and then when something crazy like this happens. But I guess this is why it seemed like a simple question. It wasn't actually simple. It was one of those, like, if you weren't watching what you're doing, you would have lost the marks. So anyways, let's get back to this question, okay? So what eventually happens is that, do I even have a free page of it? Okay, I do. So we had our red part here, boom, and then we have our 4K, and then we have our purple black part here, purple black node right here, and then we have our second one, our yellow. So we have our yellow node there, right? And then we have our other 6 and 12 in parallel. 6 and 12 in parallel makes a 4K, right? And these two are being connected to the same node, right? So this is going to be connected here to each other, because remember, as we had said previously, this is all one node. This is the node that I just drew here, right? So that's what was drawn, okay? And this is your equivalent circuit. This is what it looks like at the end, okay? You've got your 14, your 4K and your 4K, right? And this is what the final circuit looks like. So therefore your equivalent resistance is 4 plus 4, which is 8. Oh, it was a rather long-winded question. I thought it would be simpler. That gives you 8 kilo ohms, right? So yeah, this was a bit of a weird one. So just to reiterate in terms of this picture, right? Everything from here, all of this, right? All of that turned out to be one node. This was all one node, right? This is the result. And yeah, this is how it ends up being like this. Those two being parallel, and therefore this is the final circuit, what it looked like. Okay, let's do our Norton. Okay, so for Norton we short, and we try to determine because they want AB, our I Norton is going to go that way, I of Norton. So to determine your Norton equivalent, right, we need to determine IN. So first of all, this voltage source makes current, and this current is going to divide perfectly between these two branches, right, going like this, okay? So we're going to have our current here, we're going to just call it I1, okay? So I1 gets to this point, right? At this point, I1 splits into I2 and I of Norton. Right? So when we look at this, right, we must think this is the circuit that we're looking at, and we're trying to find here our IN. And let me draw it in. So this is IN, right? This is I1, and going down here is I2. Okay, so this circuit is actually also equivalent to this, right? This is your 4K and your 4K, right? Because this, you got this parallel combination going on there, right? Going like this, right? Okay, right? So therefore, for you to find the current IN, it is equal to because here you've got an equal voltage division going on, right? You've got your voltage here. So the voltage here are going to be equally divided between the two 4K resistors. So you got 7.5 here and 7.5 there, okay? Basically, this is what's happening, okay? So therefore, the current I1 is equal to 7.5 over it's equal to 7.5 over 12K, right? So remember that I1 is the current going through this node, right? You may have made a mistake where you said that I1 is 7.5 over 4K. That is not the truth, because remember that I1 is the current that's flowing through there, and because of the parallel combination, there is an equal voltage split. That is something that you need to that you need to understand to do this problem. There's a equal voltage split between the two. So therefore you have 7.5 volts being placed across your 12K, 6K, 12K, and 6K resistors. Okay? And your current I2 is equal to 7.5 over 6K, right? So this is 7.5 over 12 gives you like 5 over 8 M, and 7.5 over 6 gives you 5 over 4M. Okay, so your value for I Norton is equal to I1 minus I2, which is 5 over 8M minus 5 over 4M, which is a value of 5 over 8 minus 5 over 4, negative 5 over 8. Negative 5 over 8, which is negative 0.625 milliamps.